discussion about chemical weapons. So we thought it might be useful for you to know a bit about their chemistry so that you can understand the discussions rather better.
So I know a little bit about some of these things, in particular nerve gases, just because some of the research I do looks at the nervous system and how we can interact with it actually to control pain rather than kill anyone.
The use of chemical weapons really began in the First World War. First of all, they used chlorine, which is a sort of yellowish gas, so you could see it coming across the battlefields.
You had trench warfare. These would go along no man's land down into the trenches and obviously maim and kill the enemy, or if you got the wind direction wrong, your own troops.
Mustard gas, which is a chemical weapon which was used again in the Iraq-Iran war in the 1980s, is, although it's called a gas, it is actually a liquid, which made it particularly unpleasant because it would persist on the battlefield for months. Mustard gas that was shot in the autumn could still be there in the spring and affect people, and it caused blindness for those people who were not actually killed by it. But the rather macabre twist to the chemistry of mustard gas is that it has since been used, or derivatives of it have been used in medicine, and more people have been saved by derivatives of mustard than were killed in the various uses on the battlefield.
Run up, and in particular in the early stages of the Second World War, I guess both sides, Allies and the Nazis, they were both developing more sophisticated chemical warfare agents, presumably in case the other side used it. Luckily, although lots of developments were made, luckily there was no chemical warfare whatsoever in the Second World War, and none of these items got used. But nonetheless, the technology had been developed, and so these days there is some knowledge out there about these more advanced systems, of which sarin is one of them. Unfortunately, terrorists can get hold of it. I've got a molecule of sarin here.
Not real sarin?
Not real sarin, no, that would be illegal to make that. I've made it out of straws and these coloured balls here. Quite a small molecule, not many atoms, and that's why it's volatile. It's a gas, or a very low boiling liquid. Here we have a phosphorus, this purple one. These two red ones are oxygen, the black ones are carbon, and the thing which makes it reactive and volatile to some extent is this one here. This is a fluorine, and what this does is it blocks something in all animals, humans, called asetilkollinesteraz'ı. That's what it works on.
There was great worry in the UK that chemical weapons, which by the time of the Second World War were much more sophisticated, might be used. So all British citizens, even babies, were given respirators or gas masks. And I've got my father's gas mask. I think they were presented in a cardboard box, but my father had this rather posh leather case made for it. And if you look inside, it has his name. He's written A. Polyakov, Esquire, and he's got his work address and even his telephone number. Inside is the gas mask itself. I haven't taken it out for many years, and I think it might be perished, but let's see if we can get it out.
So what is acetylcholinesterase? Well, before I tell you what the esterase bit means, I'll tell you a bit about acetylcholine. So this is a molecule here of acetylcholine, and this is a neurotransmitter. So whenever we breathe or move our arms or do a whole range of things, heartbeats and whatnot, we use our nervous system, and our brain sends a signal. Now, throughout most of it, it's like an electrical cable, but when it gets to a junction, those signals are transferred by neurotransmitters, and acetylcholine is one type of neurotransmitter. So this drifts across the synaptic gap, the junction, and it triggers the next response, and that response might be the arm moves or lungs breathe.
I think I may need to stand up for this. So here are the straps, but let's see what's left inside.
When you want that response to die off, what happens is this drifts away from its receptor and a molecule like a Pac-Man comes along and chews this up. And that molecule is called acetylcholinesterase. So that's the totally natural, very good thing, because otherwise, if you move your arm, it would always be there. You wouldn't be able to stop it and get it come back. And again, with breathing, you'd be always breathing out and not breathing in.
There's something coming. So here we are. This is now completely come off. And there is an eyepiece and the thing that you breathe through.
So you need this to go on. And this happens, you know, in milliseconds. It's incredibly quick. And all that happens is that this acetylcholinesterase comes along and it takes that end off. This is now vinegar over here, and the other bit is choline, and that gets recycled to make more acetylcholine in the receptor end.
Well, you can't see very much. It's a bit dirty. I can just about see the camera. I couldn't drive in this, and what it would have been like walking in the complete darkness of blackouts, I've no idea.
So that process is going on and on and on constantly in our bodies. And what sarin does is it comes along, and the molecule which takes this end group off here, let's call it this thing here, it's this OH which is going to happen.
That's the Pac-Man, is it?
That's the Pac-Man molecule. Comes along, it swaps that for that, and then water comes in and takes this off to make acetic acid. Well, sarin comes along and it's got a much more active group. The fluorine is really reactive. That goes, and this attaches on, but now water can't take this off again. So it's just soaked up one of these Pac-Man molecules, acetylcholinesterase molecules. Well, now you see it's not available to break down the acetylcholine in your body. So you've always got an on switch on your muscles, and the thing which is deadly is your breathing, because obviously your lungs and muscles, they move in and out, and if they don't go one way and don't go back the other way, then you know you'll very quickly die of suffocation, which is why you see in all these news reports people with really bad breathing problems, and it's because they can't get those muscles to work correctly, because the acetylcholinesterase is being mopped up by the sarin, and the water can't hydrolyze.
Inside here will be activated carbon, charcoal, which has a very large surface area and will absorb the molecules of the poison gas. And I believe, though I'm not certain, that they found that coconut charcoal was by far the best. Why from coconut, I don't know. It just probably gave a higher surface area.
So there is an antidote, and of course whenever chemists have designed in the past poisonous things, obviously they don't want to kill themselves. They're clever guys, they invent some sort of antidote, and the antidote is this molecule. It's called pralidoxime, and this is like super water. So here's an oxygen here, and it's connected to this nitrogen, and that makes this oxygen about 100 to 300 times more reactive than normal water, and that can come along and displace the sarin from the acetylcholinesterase, and that can go about its business again.
Now the other thing which is perhaps more interesting is this, which I bought as a schoolboy in the early 1960s. As far as I remember, I paid 5 shillings for it, 25 UK pence. And 60 at that time, 60 US cents, so not very much. Inside, if you look, this is a kit, a military kit for detecting poisonous gases. And here are the instructions how to use it. Here there's a whole lab of little different vessels, and underneath is essentially what is a bicycle pump, except instead of pumping things up, it sucks air through a hole at the top. You put the chemical tester here and then you punch like this and it sucks air through. So you've got to imagine me now wearing a gas mask and gloves, because there may be chemical. It was that you put the thing in here, and then out of here you took a small paper disc. So imagine wearing gloves and with a battle raging around me, and you put a chemical, this piece of filter paper in here, and then you start mixing up solutions here and start pumping away and see if you get a colour.
Does this stuff scare you?
Yeah, totally, absolutely, yeah. I mean, it's horrendous. The lethal dose for this is around 1 milligram, far smaller than the smallest sort of sweetener pill that you might put in your coffee, for example. We think of cyanide, sodium cyanide, as being quite dangerous, but you'd need sort of half a teaspoonful of that. So you can see that these are, you know, around 1,000 times more deadly than even cyanide, and we all know that that was horrendous.
I think one of the problems of chemical weapons is that they are not targeted at particular individuals in the way that you would if you shoot a gun at them.
You can't control them. I mean, if you're aiming a bomb or a missile at a building, you're aiming at that building, but if you release a gas, it's going to go wherever the wind blows it, and there's no control of who's in the way and who isn't.
Also, that the members of society who are most vulnerable, old people, young children, are those that are likely to suffer most from chemical weapons, because if you know there are chemical weapons about and you're properly equipped, such as soldiers with all their battlefield kit, then they're relatively little danger. You cannot easily protect yourself from exploding bombs, if they're big ones, but you can from chemical weapons. So part of the revulsion, I think, that everyone feels about chemical weapons is that they're not targeted at individuals, and innocent bystanders can so easily be injured or killed.
So look at